Chapter 6, Section 6.3, Double Angle, Power Reducing, and Half Angle Formulas. Those are the objectives, using the double angle formula as well as the power reducing formula and using the half angle formula. Let's take a look at what those formulas are. Yeah, we have double angle formulas for sine, cosine, and tangent. And they're nice to prove. They're not very difficult to prove. These are identities, and identities can be proven. And I'll just mention how to do that. If you use 2 theta and you rewrite 2 theta as, so we have the sine there, as the sine of theta plus theta, you can then use the formula for the expansion for sine of a plus b, where the a is your theta, and well, b also happens to be theta, and very, very quickly you will end up with this identity right here. In a similar way, you can prove the second identity by viewing this as the cosine of the sum of theta plus theta, and as well you can view this as the tangent of theta plus theta. Use the sum formula for the expansion for tan of the sum of 2 angles, and you will immediately obtain this. It's virtually 2 lines. Now, we have 3 versions for the formula for the cosine of 2 theta, but only 1 version for the sine of 2 theta. Okay, and the reason why that happens is there are no squares here at all in the expansion for sine of 2 theta. But we have a square here, which we can replace with the Pythagorean identity, 1 minus sine squared, and that would end up giving you this identity down here at the bottom. Or we could take this and carefully, I say carefully because there's a minus sign in front, replace sine squared with 1 minus cosine squared, and in 2 lines you'll quickly have this one derived. So there are 3 versions of the cosine of a double angle. In addition, we have power reducing formulas here. Okay. These formulas actually come from previous ones, and they're simply a rearrangement of previous formulas to prove these. Now, what these do is take powers on sine or powers on cosine or powers on tangent, not just squares, but higher powers as well, even powers. And they reduce them by replacing expressions that involve powers with ones that do not have powers. So it's called power reducing. A little bit of algebra going on here, and we'll have an example coming up soon where we'll put that into use. We also have useful identities that come up a lot called half angle formulas, and these are derivable fairly simply, despite how they seem to be complicated. And half angle is represented by a non-half angle. They're called half angle formulas. So they come up in interesting ways. Now notice down here, it's very important, you see there's plus and minus in front, and often the plus or minus comes as a result of taking the square root and you get plus or minus. That's not what's going on. It's saying here that the plus and minus indicates that you must determine the plus minus sign of the trigonometric function based on the quadrant in which, and you got to look at which angle we're referring to here, a over 2. If you know the quadrant a over 2 lies, then you understand whether you use the plus or the minus signs right here. So we'll have an example of that, and we're going to do those homework problem examples right now. So let's get to the first one here. First one. If in problem 1 we have sine A is 4/5, sine theta is 4/5, and theta lies in quadrant number 2. Stop. Let's draw that picture right there. So there is a quadrant 2 angle. And the sine is the opposite for hypotenuse 5. By Pythagorean theorem, we have a 3 there. It's negative since we're in quadrant 2. Find the exact value of 3 different things. So we need sine 2 theta. Okay, so sine 2 theta by our formula sheet here is 2 times the sine theta times the cosine theta. Notice these are single angles, which we know. So we're getting a double angle value based on single values of the angle theta. 2 sine theta cos theta. So let's put that up there. 2 sine theta cosine theta. Now use your triangle to get those values. The sine of theta, opposite over hypotenuse. The cosine of theta, adjacent over hypotenuse. Now just work out that arithmetic. So you have 2 over 1 times 4 is 8, times negative 3 is negative 24, and 5 times 5 is 25. So that's the value of sine 2 theta. That's the first one being asked for. The next one being asked for is cosine 2 theta. Cosine 2 theta. Well, how do you know which one of these identities are supposed to be used? Well, it doesn't matter. You'll get the same answer by using any of the 3. And I encourage you to try all 3 and show that you get exactly the same answer. Now, we have a triangle here with all sides known. So we know the sine and we know the cosine. So it does not matter which one we use. So we'll take a pick. So say we use 1 minus 2 sine squared. Let's try that one. 1 minus 2 sine squared theta. Why am I choosing that one? No particular reason. 1 minus twice the sine of the angle squared. Remember that. Sine of theta squared is the proper way to write it, and the way we shortcut that is to write it this way. So find the sine of the angle. That's 4/5, and then we square it. Okay, so let's do out that arithmetic. 1 minus 2 times. Squaring 4/5 is 16/25. Okay. Keep going with the arithmetic. 1 minus 32/25. Okay. Keep going with the arithmetic. So this will be 25/25 minus 32/25. So that will give us negative 7/25. And that will be cosine of 2 theta. The last one we need to do here is the tangent of 2 theta, right there. So we have to do that one. So let's try that. Tangent of 2 theta. So we need our identity formula for that. Tangent of 2 theta, here it is. 2 tangent theta divided by 1 minus tangent square theta. So let's get that one written down. 2 times tangent theta divided by 1 minus tangent square theta. Okay. Well, we have our picture, so we have the values of the tangent as well. So this becomes an arithmetic problem. 2 times the tangent, now that's opposite over adjacent. So that's negative 4/3. Negative 4/3 divided by 1 minus the square of that number, since it's tangent theta and then squared. So negative 4/3 and then squared. So we just got to work out that arithmetic. So this is negative 8/3 divided by 1 minus, squaring this would give us 16/9, 16/9. Okay? So we have negative 8/3 in the top. In the bottom here, this is 9/9 minus 16/9. So that'll give us minus 7/9. Okay? and then we'll simplify our complex fraction here. Negative 8/3 divided by negative 7/9 or times negative 9/7. So we'll get that. Let's see, we could divide here by 3. So negative times negative is positive. 8 times 3 is 24. And 7 times 1 will be 7. So 24/7 looks to be the value of tangent of the double angle, 2 theta. Okay, let's see what else we have in the problem list. Problem number 2. Verify an identity. Okay, so find the exact value of cosine square 15 degrees minus sine square 15 degrees. Now when it says exact value, it means no calculator. It means algebraic. Get the answer. Okay. So how do you know what to do there? Well, I scan the formula sheet and I see if I can see the pattern there. And I see here cosine square minus sine square of the same angle theta. So cosine square minus sine square is cos 2 theta. See, we got cosine square theta minus sine square theta. So this is equal to the cosine of 2 times 15 degrees, like that. So that's equal to the cosine of 30 degrees, which we've had several times, and that's square root of 3 divided by 2. Okay, so that one's done. Problem number 3. Problem number 3, we'll need a full piece of paper to work on this one. Verify the identity. So we have sine of 3 theta is equal to 3 sine theta minus 4 times the sine cubed of theta. So we have to verify that identity. Okay. Notice these are single angles. This is a multi-angle. It's much easier to reduce a multi-angle to single angles than the other way around. So I'll work on the left side. What in the world could we do here? Well, part of the hint is that we need to reduce the angle down to a single angle. We don't have an identity for sine 3 theta, but we do for sums, and we do for double angles. Well, unfortunately, if this were 4 theta, I could call it double 2 theta and use a double sine of 2 theta formula. So I think what I'll do is I'll think of this as the sine of 2 theta plus theta. Because 2 theta plus theta would be 3 theta. That's sine of A plus B identity. So we need to get that identity from the formula sheet. And I got it here. So this will be the sine of A, that's sine 2 theta, times the cosine of B, that's theta, and then plus the cosine of A, that's 2 theta, multiplied by the sine of the second angle, theta. So that's my idea so far. Okay, now what? Notice that where we're going involves only sine, and we have cosine here. So we need to get rid of cosine. Also notice we have single angle theta, so we need to get rid of the double angle here as well. Okay, so there's a lot of work to do. So first we're going to get rid of this one right here. So this one will be sine 2 theta, 2 sine theta cosine theta by using double angle. Okay, so we got that one. That's multiplied by cosine theta. Okay, so we got that one right there. And we got a plus sign. Now we have cosine 2 theta. Okay, the problem there is that we have 3 of them. Which one of these are we supposed to use? Hint, we're going to only sign functions on the right side of the identity. So I'm going to choose this one, which only involves the sine function. And these are sine and or only cosine. So this is the one that we want to use. So replace cos 2 theta with 1 minus 2 sine squared theta. So replace this here with 1 minus 2 sine square theta. Now all of that is multiplied by sine theta. Okay, it's getting big. What can we do? Cosine theta times cosine theta, we can compress that to be cosine square. Okay, here we could distribute here and pull it apart. So sine theta times 1 is sine theta minus sine theta times sine square is sine cubed theta. Okay, well that's looking good because we have a cube in the answer that we need to get to. So that's taking shape. But notice we still got a cosine in there, and we need to get rid of that cosine. So we're going to replace this with the Pythagorean identity. Two sine theta times cosine square is 1 minus sine square theta by the Pythagorean identity. Okay, and then we'll just write down the rest of it here. Sine theta minus 2 sine cubed theta. Okay, now what? Well, maybe distribute here. Notice that we're all in sines, and we have single angle everywhere. That's what we need. Always keep an eye on where you're going to help figure out what to do now to get there later. 2 sine theta times 1, 2 sine theta, minus 2 sine theta times sine square will be 2 sine cubed theta, and we'll copy this down so we don't lose it. Okay, how are we doing? Well, we have like terms here and here. So 2 sine theta plus sine theta is 3 sine theta, minus 2 sine cubed theta and another minus 2 sine cubed theta makes minus 4 sine cubed theta. And if you look at the top of the paper, we've got it. That's exactly what we wanted to show. So we got it. That's the conclusion of part A.